Yeah, I think right now. So you are able to see my shared slide, right?
Yeah, it's showing DL division system.
Okay. I'm not seeing that. It takes some time. I don't know. But my voice is kind of audible, right? Okay,
Yeah, it's very it's crystal clear.
So you are able to see my shared slide, right? Yeah.
No, now it's some disturbance is there.
Yeah, I just turned off my phone.
No. Now it's clear.
Okay.
Now it's clear.
Okay. Okay, so let's go ahead. So welcome you all to this session. So I hope you are watching live. So for quiz 2, the syllabus is going to be content from week 5 to week 8. We are not including contents from week 1 to week 4. Given that, let's revise the important topics from week 5 to week 8. So idea is in each weeks we take one problem and we try to solve that problem with different varieties of algorithms. So keeping this in mind for each week helps you a lot. Okay. So for week 5, the essential problem that we try to solve is adaptive gradients. Okay. So the problem you can ask is when we do this optimization, often we encounter and sparse inputs. Like if you take an image, we encounter most of the pixels in an image going to be either 0 if it is a black and white image, and it happens very often in other domains as well. So when we encounter such inputs, we have to ask this question, whether using a vanilla gradient descent is better, in the sense whether it helps converge the algorithm quickly or not. So that's the question. That's what we try to answer in week 5, and we have seen that in week 5, using a gradient descent as is, okay, without taking into account of the previous history of gradients, makes a poor convergence. Of course, it converges eventually after running for 1000 iteration or 2000 iteration, but it takes a long time. Okay, so it follows a particular direction where the gradients get updated for some parameters. For other parameters, it won't get updated at all, or it gets a minimum updates. So that's what the problem is, and we try to fix that problem using an approach called adaptive gradients. Okay, so how do we tackle this? So we, since the essential idea is some parameter gets a frequent updates, some parameters gets either an update or no updates at all. Okay, based on the gradients. So the moment my input x is 0, right, because we are saying the input itself is sparse. So if my input is 0, then there won't be no gradient associated with that input. So if it is 0 for many iterations, sorry, many samples, then the weight never gets updated. So that is what we mean by some parameters gets frequent updates and some parameters won't get a frequent update. So it's kind of create an imbalancing. So we take into account the history. So the equation, the update rule remains same. Okay, so whatever the approach we take, whether we adapt the learning rate or adapt the gradients, whatever, the update rule remains same. So in my update rule, we always have this WT plus 1, the next weight, we have the current weight WT, and then we subtract the gradients. Okay, so in this case, I'm just rewriting a thing a bit, where I'm putting this T suffix for both learning rate eta, as well as, instead of writing the gradient nebula omega t, I'm just writing it as mt. Okay, so which means we are parameterizing this eta and the gradient. Okay, it's a very simple. So all the algorithms, there are variety of adaptive gradient based optimization algorithms, starting from AdaGrad, RMS Prop, ADAM, AMS Grad. So whatever the algorithm is, we are going to just maintain the history of it, history of the gradient. So this is the one important thing that you have to remember. Okay, so if you want me put this symbol, okay. So we always have this gradient at time step t. We compute this, okay, and then what we do next in adaptive gradients is we have this parameter, then we square it, we keep that one as well. So we are going to make use of these two quantities in order to update my weight values. Okay, why these two quantities gives me which parameter gets more frequent update and which parameters gets less frequent updates. Okay, so this is an indirect way of counting this number of updates. So essentially what happens is that now my learning rate, okay, we call this as an effective learning rate. Just to distinguish from learning rate schedulers and constant learning rate, we just call it as an effective learning rate. My learning rate becomes function of, keep this in mind, okay. Now I have my gradient computed for each time step, and also I have gradient square. My learning rate is a function of gradient square, okay. My current gradient square, and then one step before, and then two steps before, and all the way up to all the gradients computed at time step t. Okay, we call this as a history. And my mt, that is that keeps tracks of the past gradients, is function of the gradient alone. We are not using gradient square. So this is going to be true for, you can cross check, right? This is true for all type of adaptive gradient based optimization algorithm. Okay, so what is this function usually? Okay, I take these two quantities, the current gradient and the past or the history of all the gradients, and I also square it. I have these two quantity and I pass these two quantity through some function to compute my learning effective learning rate eta t, and also mt. Okay, so this function, you can see that this is going to be some sort of averaging. Most often it is going to be exponential averaging, okay, that we have discussed in the lecture. So this exponential averaging, either some algorithm uses this bias correction like in Adam, some don't use this bias correction. Okay, so this is the crux of the entire week. So we come up with a variety of algorithms by manipulating only these current gradient and history of gradient and gradient squares. Then we encounter some, even if we make use of this, then we encounter different sorts of problems in each algorithm, and we try to fix them by making it more complex. Okay, for example, I just took two such algorithms, even though there are some 6 to 7 adaptive gradient algorithms. So one is the simplest one, right, is Adagrad. Adagrad, again, if you look at this update rule, if you look at this update rule, now you try to correlate. Okay, again, this is the update rule we are discussing, and we have this current gradient, and I call this in the previous slide as eta t, because somehow it is function of t. For each iteration it is going to change, and all these together I call it as, or we call it as, effective learning rate. And we said this eta t is function of gradient square, not the gradient. Okay, it is true for all algorithms. You should not use the current gradient, you have to use the gradient square. So it is going to be del omega t square all the way up to del omega, not, it takes all the points, entire previous history. Okay, and what is this function here? So this function is an inverse function. Okay, so I take this inverse of vt. This vt is proportional. This vt keeps track of my history. Here we are not taking exponential averaging, instead we are simply taking kind of rectangular averaging. Okay, which means we give equal weightage for the current gradient as well as all the history. Okay, so one possible confusion that I observed, right, is most of the time you get confused, and also we have no other option sometimes. So either we can start the iterations from t is equal to 0, or we can start from t is equal to 1. So these are all two options, and we switch between these two based on the convenience of the algorithm. Okay, so for this case, the updation rules looks quite straightforward and no complexity is involved. But when we talk about NADM, then using t is equal to 1 or t is equal to 0 seems is kind of favorable. Okay, so when I use So how do you figure out whether we are using t is equal to 0 or t is equal to 1? So either we can explicitly mention the iteration starts from t is equal to 0, or we don't mention that. Instead, we may give you this, say, v minus 1 is equal to 0, something like this. Okay. So when I say v minus 1 is equal to 0, it automatically implies that t starts from 0, because the moment you put t is equal to 0 here, then you end up with v minus 1. Then all the iterations are with respect to t is equal to 0. Then you compute t w1, w2, w3 like that. And then we also give this gradient. Okay. So we have to give this current gradient values. Of course, we can either give you this gradient value, or we can give you some function of the gradient value. That doesn't matter. So finally, you have to, or you end up with using these two equations. Either we ask you to compute the gradient and update the parameter, or we ask you to just compute the effective learning rate eta t alone. Okay, based on the questions. So this ADA-grad is straightforward, and of course there are so many adaptive gradient algorithms are there. So you need not to kind of memorize all these formulas. Okay, so of course for ADA-grad it's not that much difficult. You can remember it once you understand how it works. But when you go for very complex like ADAM and NADAM, it's quite difficult to remember all this. So in such a case, we give you the update route. Okay, so our aim is not expecting you to kind of remember all these equations. This is quite difficult. In such a case, we list out the required formulas. Okay, so that maybe we can list out the formulas with, and that may not be useful, but among this, say for example, we may add some more quantity. You may not need to use that particular equation, but it is up to you to figure out whether it is useful or not. But we always list out all the required formulas if it is too complex to remember. Okay, so we start with ADA-grad, and we discuss the problems with the ADA-grads. So of course I can just talk about that bit. So the problem is that we keep accumulating VT without giving, or we are giving equal weightage for my current gradient and all the previous gradients. So my VT grows quickly, and it always keep growing. Okay, it never stops. Either it keeps growing and may remain constant, it will never decrease. Okay, so this poses the problem, because due to this, my effective learning rate will never increase, even if I reaches some gentle surface where I'm expecting the learning rate to be high, because my gradient is going to be low. But that is not possible if I use ADA-grad. When we have very deep network, then oftentimes we may end up with some gentle surfaces where the slope is very low. Okay, so ADA-grad can't help you there. So we modify this, and then we propose RMS grad, where we incorporate this exponential averaging, but without bias correction. We could have done the bias, and also remember, if we add this factor 1 minus beta 1, we need to do this bias correction. If we don't add this factor, we don't need to do this bias correction. So that sort of things you should have learned. We may ask questions like this, whether the following update rule requires bias correction or not. We can change any quantities here, and then we simply ask you, right, whether do we need a bias correction there or don't we need. So you should be in a position to justify it. Okay, so what do we mean by bias correction? Why it is getting introduced in this equation? Do we need to correct it? All sort of things you have to figure out. Okay, so this is the crux of the entire week. Okay, this is the problem we're trying to solve. And maybe NADAM is quite difficult to understand in the first attempt, because the looking ahead is quite not clear, but you don't need to bother about that too much. But what you have to remember is whatever that I just talked just before. Okay, and this is for week 5. And yeah, so if you have any questions from week 5, you can ask now, or shall I just cover
No, sir. I have 3 questions regarding week 5.
Yeah, please go ahead. That's better too.
Yeah. So in AdaGrad, like sir specifically mentioned that we use square root of x so that the value do not get too large, right?
Yeah, not necessarily square root is not just to control the value gets too large. Of course, we don't have much answer to that. If you look into the original paper, the square root comes as a consequence of manipulating the equations. But one thing that we can argue is that the square root is actually a monotonic function, so removing that won't do any harm. But if you remove square root, it is not working. So that is the observation. So we try to give you a justification because it is growing very rapidly, something like that. Okay, it may grow rapidly, but how do you say the gradient, unless the gradient is greater than 1? Okay, my gradient value can be negative, positive, but when I squaring it is going to be positive, but it can be range from 0 to, of course, in principle, it could be infinite. So suppose if I use, say, for example, sigmoid function throughout the entire network, then my gradient values are restricted to this region, 0 to 1, even it is 0.25. So if my gradient value is between 0 to 1, right, then squaring it won't kind of uh, make it bigger, but accumulation makes it grow. So that's the justification we have so far.
Okay, so like why don't we try like higher values?
Which higher values? No, that's not required, by the way, right? Because one thing is we want to make it positive. Even if the gradient is negative, we want to make it positive. The reason we try to keep track of the number of updates through this accumulation, right? So if you go for higher values, then as you know, if
Sir,
my
in square
gradient
root.
the square root is one thing. Sorry, which one?
No, yeah, if we use like a cube root instead of square root, what are the effects that will happen?
Uh, so unless we do an example, so I don't know the exact answer. What will be the effect? If we go for higher order root, it will shrink the number too quickly, right? So that is the one thing that is the consequence. But unless we make an experimentation with that, we can't, you know, uh,
Right.
give an answer to
No,
that.
I am asking this because what happens in the like consecutive updates that since we have a very large history and very low gradient, the learning rate also becomes very low, and then we move very slow,
Yes.
right? So if we are using higher order routes, then that will like curb the large history, so somewhat negating the effects.
Yeah, that's fine. But is that always good to reduce these values, too much by taking cube root? We don't know that, right?
Okay.
See, if I am on a gentle curve, right, I am
Okay.
computing the gradients. Now I know the slope itself is quite low in a gentle curve. Now I want to increase the learning rate. If even if I don't, I'm unable to increase the learning rate. At least I want to learning rate quite to be quite higher than using the cubic root at that point, right?
Yeah.
So,
Uh,
so that's why we
yeah.
analyzed the gradient profile and see how it actually helps.
Okay. Also, there was a slide that mentioned that which which of these things to use, and it said that using Adam is common function. So why don't we use adaptive learning Ada delta, something like that?
Sorry, so you are asking adaptive learning rate schedulers, or which one you are trying to compare? You are comparing two different adaptive gradient optimization, or the adaptive learning rate schemes and the adaptive gradient optimization?
So in one of the in like lecture 5, I believe there was a slide which was titled as $1 million question.
Yeah, yeah.
Uh,
So where
Yeah.
we
So
actually recommend to use Adam.
yeah. So why don't we use ADA delta, something like that, which has adaptive learning? Because see, Adam is slow, right? Adam is slow than ADA delta, which we saw after the in that animation after
Yeah,
that
yeah,
slide.
yeah. So either you can use, you can use any adaptive gradient based algorithm. That's not a problem. So the only thing that we have to keep in mind is that what is the computational load? Okay. So if we use ADA delta, how many things we are keeping track of? We keep track of
UT
steps
and
for
VT.
the, yeah. So we are keeping track of the kind of manipulating gradients for both the numerator as well as for the denominator. So it increases the computational load. That, we need more storage to do all these steps. That is one point. The other point is that it is generally observed that if you use Adam as my initial optimizer, and people have observed that the algorithm converges quickly, and we don't have any reasons for that. Even we don't have any analytical reasons. We have only the empirical evidence. So whenever we start with Adam, it converges much better than the other algorithms. Maybe NADAM also converges much better because it is no way different from Adam. So either we can start with Adam and NADAM, and then we have to see whether it works. If it
Okay.
doesn't work, then you have to check with other optimizers. It is not mean if Adam doesn't converge, then no other algorithm is useful. Something like we can't. That is not implied in that.
Okay. Okay. So last question for week 5. Where does this bias correction term comes from? Like I saw that calculation.
Yeah.
So it does come from there when we take exception and then we use that we use series, geometric series to find the sum. But like, is there any intuition from where that come from? See, I know why we use bias correction. We use so that our initial gradient is not too large.
No,
But
we
like,
are actually, yeah, not too
yeah,
large. See, I think one. So in order to answer that, so if I remember correctly, moment after that, there is one more slide where we actually talk about not with respect to optimization, in general estimation. Okay, we have these points.
yeah, I saw that.
Yeah. So that is the intuition. Uh, that is an exact reason why bias correction is required in any estimation, not only for optimization, in any estimation. So the thing is that I have a true function that starts from here. Okay. I know the function is not starting from 0. It starts from here and it is corrupted by some noise. Okay. This is my true function, and these dots are kind of my observation that is corrupted by noise. So it looks like random. So I am building an estimator that recovers this true function through this exponential averaging. So when I incorporate this term 1 minus beta 1, okay. Okay, so
Okay.
where beta 1 is, I'm not sure whether it is 0.9 or 0.999 something, okay. Then 1 minus beta 1 is kind of near 0.001, right? So what I'm doing is my initial point is actually here. Okay. This is the point that I'm going to use for my initial estimation. This is the first point that is coming into my algorithm. My initial point value is, say, for example, it is sitting at 5. But because of this multiplication by this 1 minus beta 1, I'm pulling it down to 0. Okay, which means it gives me a wrong picture that my initial value starts from, because if you multiply 5 by 0.001, it's very low value. So my estimator assumes that is my initial point, and from that point onwards, it tries to estimate the true curve. So it takes some time. After taking some n number of points, it tries to come up with the true function. Okay, so after some iterations. So if I do bias correction, it quickly, merge with this, come up with this true function. So that is the exact idea why this bias correction term is required. It doesn't mean if you don't do bias correction, your algorithm never converges. In some frameworks, I think if I remember correctly, in Keras, they don't do bias correction for ADA. From this point that it's unnecessary computation because we have billion parameters, you are multiplying all these parameters by one constant, so it's a billion multiplications. So again, it's a design choice.
Right. But like, how will you like with this intuition? How will you come up with the term that we should divide we should divide M with 1 minus B1?
So that's a derivation, but again, if you look for some intuitive explanation, right? So what I'm doing is my initial point is here. This is my del omega 0. I am just pulling this unnecessarily.
Yeah.
Give me a second, please.
Okay.
Okay, sorry about that. So you are able to understand this, right? So what this factor actually does to my initial gradient. So it is unnecessarily pulling these values to near zero. So how do you counteract this?
Okay, so we try to null that value. We try to divide it by say around same value, so it becomes 1, something like
Yeah,
that.
yeah. So we have this 1 minus beta 1 t. Okay, then of course I don't want to. This factor almost kind of becomes 1 after some iteration. So just for some few initial iterations, we need to this stuff so that it actually make use of the original observation del omega t.
Okay, so we are trying to negate the effect of 1 minus beta 1.
Yeah, that's the
Okay,
kind of straightforward answer. Yeah.
Okay, thank you.
Okay.
Also, sir, like I'll join later. So sorry for the question. But which weeks will have more focus in the paper?
So if you really want the answer for this question, I would say it is week 8.
Week 8.
Yeah,
Okay.
because the week 8 is quite dense and this focus is around week 8. The maximum focus. But
Okay.
as far as deep learning is concerned, I don't know, we can't compartmentalize each week because all from the conceptual viewpoint, all of them are connected. So I can't say this question only belongs to this week. This question connects with all the previous weeks. So it's a kind of, if I ask some question from backprop, right, or based on some activation function, then it belongs to week 4 onwards. So this is a kind of message that all of you might keep this in mind. So it's not something like when I frame these questions, I don't even bother about assigning weightage to each week. It's like a common question that requires the knowledge from the previous weeks. Maybe 1 week or 2 week before, doesn't matter, but you need those knowledge in order to answer some questions in this week. So it's a kind of that is how we set the paper.
Okay.
So
Thank you.
yeah. Okay. Yeah. So now this is all about week 5. The key takeaway is summarized. And just moving forward with week 6, we talk about this regularization techniques. Of course, again, what is the fundamental problem that we try to attack or we try to solve? Okay, so to put it in words, we can say I train my model on a training set. It outperforms, gives a high accuracy, but the moment I put it use a test set or put it in the real world, it underperforms. Okay, so it naturally it leads to this question: what happens? What is going on? So how could my model performs well on training set, but poorly or underperforms on the test set? So we try to answer this question analytically. So that is where this regularization comes in, and that is where we talk about all these from the traditional machine learning perspective, all this underfitting, overfitting, all these stuffs. So to answer this question, we need to introduce few parameters, and like in the previous case, right, we have a common update rule, and then how we incorporate the history so that there are variety of algorithms. Okay, there emerges variety of algorithms that helps those problems. In a similar way, the one question that we try to, one quantity that we try to find or try to answer is, of course, usually all deep learning models have billions of parameters, only millisum sample. So we have a definition for complexity. There are variety of ways we can measure complexity, but here we are taking the parameters of the model to measure the complexity. Okay, so we will come to that later. So what is that one question that we try to solve? So since it is about the error, right? So my model performs good on training set, really bad on test set. So somehow I am trying to compute the error or the average performance of the entire model. Okay, both on training set as well as on the test set. So this includes, this quantity is for both training as well as test. So this is the kind of, this is the equation that we try to solve. So in order to solve this, of course, we took this important concept. Okay, so we introduced this bias, variance, and then this irreducible error, and then we necessarily talk about these things, this bias and variance, in order to interpret the solution of this equation. Okay, so this is, yeah, this has a long history. Introducing this in the statistical estimation theory, it is there, so we borrow it from those domains. So what is bias? So you have to keep this in mind. So I have a true function f of x, and also I picked up an approximation for that function that we denoted by f hat of x. So of course, we demonstrated all these things using simple examples of linear models and then polynomial models. And then the same thing holds for deep learning models as well. The only thing is that now it is really more complex composite function. But the key takeaway, we don't bother about those form of the functions, only we bother about the true function and the approximation. Okay, so we call the bias as expectation of approximation minus the true. So of course, we can give a definition for that. What does that mean? That all these concepts we have discussed in the lecture, but the key takeaway is how do we compute the bias? Okay, so this is with respect to, there are two functions involved in computing the bias. One is my true function, the other one is my approximation. And I'm just, since one thing is this, usually when we try to compute the expectation, if we have the probability distribution of all my trainings and all for the entire data set, then we can use that probability density function to compute E directly, but we never have that. Okay, we don't have this probability density functions for my samples. So again, we are approximating this or we are estimating this expectation. Okay, so I try to measure how far my approximation deviates from my original. Okay, so we are comparing my true and then approximation in computing bias. And in variance, we do this quite differently. In variance, we are comparing the approximation function with itself. So how do we compare this? So I change my x little bit, then how far my approximation changes. Okay, or in other words, we say whether it is too sensitive to change in x. So if it is too sensitive to change in x, then it must have high variance. Okay, so ultimately we use these quantities to find the answer for this expectation of y minus f of x, that is mean square error over all the samples. Okay, not just training, not just test, not that observed. In fact, that is the true sense, not that observed. It is actually a distribution over, or it is actually a probability density function. Okay, So we have only an observed samples. We split into train and test, and we make use of them in order to at least give an justification why my model underperformed on the test set. And then we discussed. So this is very important. Okay, so as far as this week is concerned, understanding this bias variance and then coming up with this regularization term is the kind of, I would say, though the contents looks very big for this week, but the entire thing or entire important thing is consolidated within these concepts. Okay, that is where you need to focus. The rest, different types of regularization, you can just give a, whoever, just you can go through them. You need not to do much about that, but you have to remember these things. That's why I'm just displaying it here. Okay. Of course, now we have an observation, and for the time being, this is of course evaluated on the test set. It can be trained. Either you can consider a training sample or a samples from the test set. Okay. So now we have to justify why using training set alone does not captures the true error. Okay, so the true error is that we have just displayed earlier, that is my y minus f of x. This is my true error. We can't compute the true error at all because it requires the probability density function that generated all those samples. So this is quite impossible. So what we have is we have some observation. Then among those observation, we divided the observation into train and test, and then of course validation. And we try to figure out which one actually closely approximate my true error. Okay. And then for all this case, we end up with this equation. I mean, this is an empirical estimation of all this, and this sigma square is inevitable. The only thing that determines everything, okay, is this factor. Okay, if this factor becomes 0, that is good. Okay, if it is not becomes 0, then that is bad. So in the sense, okay, so for both training set and test set, we see what happens. Okay, if this factor becomes 0 or not 0. So this, we can't do anything about this sigma square. It is always there for both training set and test set. But what happens to this covariance term for test set and training set? So for test set, it becomes 0. For training set, it exists. Okay. So that's why we say my training set alone does not give the true picture of my true error. Okay. So we try to approximate again this term, because to compute this expectation, again, we need the true probability that we don't have. So again, we need some sort of approximation. So that's where Stein's lemma comes into the picture. So overall, we have this beautiful curve that summarizes everything. Okay, so we have model complexity on the x-axis, and of course, as I mentioned earlier, when we talk about model complexity, there are different way of measuring the complexity of model. I don't know all of them, or even I just know 2 of them. Okay, so what we are dealing here is with respect, which I will display it later. Okay, so of course, the blue curve is train error, and the red one is, or the orange one is the test error. I hope you know this high bias. Why we call it as high bias? Because no matter, so the important thing is you focus on the x-axis. Okay, so my model complexity is kind of low here. Okay, so you can think of my model complexity ranging from 1 to say in practical it could be, if I use the number of parameters, then in practical it could be 1 billion or something. Okay, of course you can normalize all these stuffs, but just sake of understanding, let's say something like this. So if my model has only few parameters, but if I have large samples, okay, and obviously those parameters are not sufficient to represent true function, so they end up creating a huge error. Okay, so and also keep this in mind, that these terms, right, bias square plus variance plus some irreducible error. Okay, so my error becomes high even if any of these quantities becomes high. Okay, so if my bias increases, then the error increases. Okay, so that's what we see here. My bias is high, so the error is also high. Then we keep increasing the model complexity. So in the sense, we are increasing the number of parameters so that the composite function becomes too complex. Okay, the nonlinearity functions composed by one after the other becoming too complex. Okay, increasing the parameter means we are making the function more complex, and the more complex means the ability to represent many functions is increasing. Okay, so I just would like to add one diagram here, say something like this. Probably you might have encountered this earlier. So I have a space of functions, okay, my true function, let's say fx, and then I have a subspace within that. So if I take my model as simple linear model, say mx plus c or wx plus b, whatever, then this model can represent only a few subset of functions. So if we make very complex functions by increasing the number of layers in the network, then that function has huge expressivity. Okay, so in the sense, if my true function is really complex, then my model is able to come up with the true function. Okay, so that is how we tie up this number of parameters with the complexity, and then this complexity in turns explained using this expressivity of the model. Okay, but in fact you need not to bother too much about that, but I'm just highlighting it here. Okay, yeah, so we are actually interested in this term, but this term cannot be computed because we don't have true f of x, that is the true probability density function. Then we have this approximation, okay, that somehow relates this with this quantity. And again, with this computing this term itself is not quite straightforward. Okay, so we approximate this term using this regularization term. Okay, so that somehow we try to do this approximation. So this regularization term omega theta, okay, is actually related to this term. So these are all the only important things that you have to focus on in this week. Okay, try to understand the entire derivation, try to grasp, uh, you watch this lecture 2 to 3 times and try to understand everything, each and every word that Professor Mitesh is talking about, and each and every word in the slide as well. And of course, once we come up with this regularization term, then we can, I mean, this is one such possibility. This is omega of theta, okay, and then we call this L2, and then there are L1 regularization, and most probably these are quite straightforward. The moment I add the regularization term, then my gradient with respect to loss changes, then my update rule changes, and you try to explore. Okay, so one thing that I would say is, if my W is equal to, say for example, I take W is equal to 0.5 in one model, and also say W1 and W2 is equal to say 5. There are two parameters, and when I add this regularization term and update the parameters after computing the gradient, all these stuffs, so which parameter gets updated most? Okay, so if my 0.5 changes from this value to, say for example, 0.4, this is a small update, but my 5 changes to 2.5, then this is a large update. Okay, so these kind of things that is expected, even though it is not discussed so too much in the lecture, but we hope these are all the things that you can, once you understand this equation, and if you ask questions based on these concepts, so you should be in a position to figure out the answer and come up with some reasoning to answer any questions. Okay, so that is expected from you. And of course, the important diagram for this L2 regularization is this, and you try to understand what this diagram implies. So this is very important, and what regularization actually does to my solution for unregularized loss. Okay, so this is actually in fact discussed in detail in the lecture. So please do watch this in case if you have confusion. And how do we measure the effective parameters? Okay, so how do I say after putting this using this L2 regularization, then the number of parameters get reduced. Okay, and pay attention to these words. It says it is shrinking, then ask the question, is there any possibility that my regularization actually expands any weight values in the network? Okay, or instead of scaling it down, whether it can scale it up? Okay, so these are all the questions you have to ask yourself. Okay, because we can frame questions around these words. Okay, so you can just, instead of just going through these words and taking it for granted, you just contemplate and reflect on all those important words or adjectives. Okay, so that's all about week 8. And of course, after this L2 regularization, you see so many regularization techniques, and all of them are connected with this concept, expectation of y minus f of x squared. Okay, because this is the core equation that we try to solve. And of course, you can modify the x with some noise, inject the noise, or you can modify, sorry, not here, but in general. Okay, and then you see what happens in the estimation, and you can inject the noise in the output and see what happens. So fundamentally, you make use of these equation again and again. Okay, whatever the modification you do. And of course, a few more techniques we just walk through. I mean, not in detail, just big picture like dropout and then ensemble methods. Okay, and of course in ensemble methods you might focus, because we are trying to reduce this bias and variance. So especially we try to reduce the bias as well as we try to reduce the variance. So how each of these techniques help us achieve these two tasks or these two objectives. Okay, so that is the core thing in week, I don't know, week 6. Yeah, week 6. Okay, so that's all about regularization techniques. So if you have any questions around this, you can ask, or I just move on to the next one.
Okay, sir. Can move to next week.
Okay. And so next one is, once again, even though we talked about pre-training, layer-wise pre-training, all these stuffs, that's kind of quite old. So we are not going to focus on that part. So for this quiz, you can kind of just walk through those concepts, need not to pay much attention to, but you pay attention to activation functions and what are all the takeaways that, what are all the important things that you have to keep it in your mind is that we discuss all the activation functions with respect to this chain rule. Okay, again for this thin network, not wide network. And with respect to using this equation, we answer some questions, right? And how the saturated region in activation function causes some troubles. Okay, so especially when we have this logistic and then tan H, we have these saturation regions, and how it actually hinders the learning process. Okay, in essence, how it introduces this vanishing gradient problem. And how it is connected with this saturated region of the activation function. So these are all few things. And one more other thing is how zero centering is helping us, okay, or why it is expected. So whatever the properties of the activation function, so it is are all connected, okay, to this single equation. So understanding the activation functions and able to correlate with this equation is the expected skill from you. So we can frame questions around these concepts. Okay, and this understanding is extremely important. Please do not think that once I solve so these practice assignments and then graded assignments, if I know the steps for that, that is enough for quiz. That's not the case. Okay, so we expect you to understand all this, then we may frame questions around this understanding. In fact, I may not look at whether this question has any correlation with the gradient assignment or practice assignments. Okay, we frame the questions keeping this in mind, whether a student understood this particular concept or not. So that is our key exploration. Okay, so if you have a good understanding about all these things, then you should be in a position to answer those questions. Okay, and finally we have this connects. Of course, I don't want to again elaborate on it. Connects, there are a lot of concepts involved in the connect and quite new to you, new to all of you, if you are new to DL. Okay, and what is there in ConNet? ConNet is a kind of, we have only two layers. One is a convolution layer and the another one is a fully connected layer. Fully connected layer we already knew well. Okay, how everything works in fully connected layer, how to compute the gradients for each neurons in the fully connected layer. So same thing is expected for convolution layer, and how weight sharing helps in kind of many aspects, right? Reduces the number of parameters. That is the one key goal of sharing weights. And what are all the hyperparameters in convolutional neural network? Even this number of kernels per layer itself is a hyperparameters. There are no thumb rules. Sorry, there is no theoretical justification for number of kernels, all these stuffs. What you need to know as far as this, I'm just highlighting these three. There are many things. One is that given the kernel, and you should know how to compute the convolution sum, and you should know how should you, what will be the output dimension, okay, of my feature map in the for different values of padding or zero padding, or this varying the stride values, all these things. Okay, so you have to know all these stuffs. That is what expected, and these are all quite trivial and enough to it's not quite difficult to understand. It's straightforward. You can use the formulas. That is always better instead of manually working out all these steps. And then there is an 1D convolution. So how it actually helps, so where it is used. If I use 1D convolution, how the number of parameters changes. Okay, so these are all the things that you have to focus in week 8. Of course, there are other concepts like guided back propagation and visualizing activation functions, deep dream, all those steps. Of course, those, once you understand all these things, right, that's not a big deal. So we don't ask any questions from those sort of concepts. Okay, so that's all about concepts.
Sir, I have a question.
Yeah, Aditya.
Sir, first question is about zero centric, sir. Sir,
Zero centering.
I
Okay.
do not understand. Yes, yes.
Yeah.
I know it's kind of both positive and equal type of graph from both positive half and negative half, but actually how it is helpful.
So, one thing is that, right, always in deep learning is we focus on three aspects. The one important aspect is whether learning happens, okay, throughout the entire iterations, okay, or whether my model keep converging to the zero loss, okay. So how this learning is, how when do we say actually model learns something? Only if my weight gets updated, right?
Yes, sir.
So if my weight get updated for each iteration from the previous iteration, then I say my model is learned. Not just a single weight, actually all the parameters in the network should get updated, okay, with their respective gradients. So whatever that hinders this process, we figure out this process and we try to come up with some solution, okay.
Yes, sir.
So if you ask particularly about zero centering, again, so far we have only this explanation, okay. Even Relu is not zero centered. Zero centered is not major problem, but the problem is that as discussed in the lecture, the region that it covers, right? So if I keep if I look at the activation value and also the gradient, okay? For example, one thing is the gradient profile, both tan. You might have seen this gradient. This is a gradient profile for logistic with a magnitude of 0.25, and this is for tannage. Okay,
Yes.
both are kind of symmetric. So the difference is that this is again the gradient. It boils down to this point. So this is the only reason that I have seen why zero centering is helpful. Okay, so even I try to generate some animations by capturing the gradient values and then plotting it and put it in the lecture, but for 2D I'm not able to come up with the configuration that actually shows this difference. Okay, so my gradient is always going to be positive. Okay, you can see that, right?
Yes.
So this is my gradient. Sorry, this is my sigma, gradient of W. This is going to be positive. So if my solution is here, so the two roles is that my learning happens good if my initialization is good. Okay, if I am lucky enough, if I initialize the points in a correct location, then that's fine. Suppose if my initialization is not at the correct location, my true solution is somewhere here. Okay, so what gradient actually does, you can see from this contour trace that wherever you start, it try to converge to this optimal point.
Yes.
Right, wherever you start from, it will converge given running it for enough number of iteration. But if you don't do this zero centering, okay, so what I think I need to open this lecture. You see this zigzag path, right?
Yes. Yes.
So were you able to justify why this zigzag path actually occurs? I mean, after seeing that,
Due to gradient, sometimes it will come positive, negative.
Okay, so I think I have to use that picture in the previous thing. Okay, now we have this equation. Okay, I try to actually we are focusing this quantity. Okay, so let's say I am here, I am focusing this quantity. Okay, suppose that my gradient comes here, dou L by dou W2 or dou H1 is here. Okay, and also I need to write this W2 as well, or the update rule for this W2. So the update or the gradient of W2, and by the way, okay. So the gradient of W2 depends on two quantities. Which are those?
So
to compute this,
W gradient of W depend on W H2 and W3.
so it depends on H1, right? And then
Okay.
what is this other parameter? So there is another parameter dou coming in. H1 is direct, the other parameter is coming in.
Gradient of A2?
Yeah, so that's the gradient of A2, right?
Right.
So that's gradient of A2. So you actually need to focus this one. So if my H1 is positive, my H1 is always going to be positive, right? If I use not zero-centered activation function.
Yes.
So this quantity is always going to be positive.
Okay.
assuming that all my neurons in the network are sigmoid. Okay. Then even if I back propagate the loss, right? What happens to this gradient then? See, this W3 also plays role. Okay, even though my sigmoid is, so I just want to explain the same concept. Even though my sigmoid is between always outputs the positive value, but my W3s or the weights in the network can take negative values, right?
Yes, sir.
And they can change the gradient. But the observation is that this quantity is either always going to be positive region, or negative. If it is negative, it is going to be negative. Okay, it will be in whatever. If it TLW and DB, sorry, DOB, if it is either they occupy these two regions, positive or negative. If there is a situation, right, my optimal solution is here, then it has to take this for each update. Okay, so when we have to keep track of the update for this, or we have to keep track of this del W2. Okay, so for each update, it has only two possible direction to move. Okay.
Yes.
So I'm not sure. Are you able to follow this up? So this quadrant is not straightforward
Yes.
because of these multiplications. So it has to move down, and then or this either negative. Which one is negative by the way? Am I writing? Yeah. So this one negative, and this one is negative positive, and this one is
positive, negative.
Yeah, positive. X is positive and Y is negative. Okay. So if my solution is in this quadrant, then if my output is not zero centered, then it's like updating the vectors. Like, so all my vectors that I'm adding in, right, I have vectors like this, then all my vectors are either help me move in this direction or move in this direction, not in the diagonal direction. Update rule means we are keep adding all those vectors. It will eventually we reach this point, but the problem is that the path it takes is going to be zigzag instead of a kind of a short path. Not short path in the sense by kind of diagonal movement is not allowed in this case. The moment I make it zero centered, then what happens is that my H1 can either be positive or negative, because my tan H now outputs the value in the either positive or negative. So what happens is that now these two movements are allowed. These two quadrants are allowed, and it can kind of, instead of taking zigzag path, it converges a little bit faster. So that, what I suggest is that you see this quantity, how this dou H1 by dou A1 changes, and unfocus on the parameters associated with these neurons. This diagram itself is sufficient. Okay, maybe my loss is always going to be positive value, and then when I back propagate, I would suggest you said W3 is equal to some negative value -1, and W2 is equal to some positive value, and then see how this gradient. So I try to, maybe this is a good task for me. I try to come up with some write-up with different values and see how this zigzag path actually emerges for each update. Okay, that might help you.
Sir, is Gelu or Relu is a geocentric?
Relu is not zero-centric.
And Gelu?
Gelu, I don't remember the equation of that one now.
Gelu,
Zero-centric
one
is
if x greater than 0.
No, they
Zero
make it
is
zero centric.
less than equal to zero.
Okay, by the way, so I will give you this since I remember the the pictorial representation of these activations. Only sigmoid and relu is not zero centric. Other things are allowing a negative gradient to flow, but they don't zero center. Like leaky relu won't do this zero centering. But either this gelu or selu adjust this curve such that because this is a curve and this is this is also a kind of curve there, right? If I remember that correctly, one of these two actually allows this to be zero centering. I think
So,
I may.
but curve for Gelu is not in the negative region, I think. So
Which one?
if the Gelu.
Okay. No, I think
uh,
Gelu was in the negative region. Okay, let me.
Gelu Selu was in negative region, and Leaky Relu was in negative region, and Elu was in negative.
Is it? I don't think so. Okay, anyhow, let me take a look into that. Where is it slide?
Say equation was of Gelu was if x greater than 0, it will be 1, and if
Okay.
x less than 0, it will be 0.
No, that's not the equation. I mean, that is.
That's not
I think
the equation.
that is the motivation how the Gelu function is actually developed. If I remember it correctly, which week is that actually?
Uh, it was in week 7.
7. Okay, just give me a second. Yeah, here. Probably it is around coffee. Maybe Kirelu exponential.
After that, yeah, this is
No,
the
this is not
equation.
actually like equation for Gelu. So here we just try to motivate why Gelu is kind of merging two functionalities that we are interested in.
So what will be the actual graph of Gelu or equation?
This one is the actual activation function of Gelu.
Okay.
So here we are just motivating how the kind of dropout, are incorporated into Gelu by default. So the final equation is this one,
Okay.
or whether, of course, for computation we can use this
Okay.
x into sigmoid of 1.702x.
So here Gelu is geocentric.
Yeah, it
If
actually.
if we give a right value of x. Okay, sir. So there is also question practice assignment 8, question number 5.
Practice assignment 8. Practice assignment, you mean? No, so what is, can you read out the question?
Yes.
Sorry,
One
week?
minute.
Which
Week
week?
8.
Week
Week
8.
8.
Okay, week 8
Yes,
I have.
week 8.
Which question?
Question number 5.
Okay, consider an input image of 100 by 100 by 3. Suppose that we use 10 kernels, each of size 1 by 1, 0 padding 1, straight value 2. How many parameters are there? Yeah, what is the doubt? Aditya?
Sir, actually, when I try to calculate by using the formula or W into H into D into number of factors, it gives
Okay,
me large value.
so it gives
Very large value. So when we calculate W by using the formula W minus F plus.
see then. Okay, by the way, I write it down here. So I have an input image of 100 by 100 by 3. Okay, I think this is.
So I couldn't. Hello.
You're not able to see.
No, I can see.
Okay. What I'm saying is that, okay, so I have 100 by 100 by 3 input image, but the
Yes, sir.
parameters are associated with the kernel, right?
Yes.
So I am using 10 kernels, each of size 1 by 1. Okay,
Yes.
so I have only 10 kernels, and the kernel dimension is 1 by 1, spatial dimension. Okay, then what will be the depth of this kernel? The depth is going to be 3. Whatever my input block depth is going to be the depth of my kernel. So it is
Yes.
going to be 1 by 3, right?
Yes, sir.
Using stride or whatever padding doesn't matter for kernel. So number of
Okay.
parameters in a single kernel is 3 plus 1 for bias. Okay, then it is going to be 10 into 40. Is it there? I didn't include the bias, is it? So which
Yes.
one is the right answer, by the way? Let me check the answer. Oh, what is the right answer? The
Actually,
30.
yes.
Okay, so I might have excluded this bias term from the computation. But the thing is this. Okay.
Okay. So when we calculate the number of parameter, we include weight and height of the kernel, not the. Okay, sir.
No, you have to include width, height, and the depth.
Of kernel.
Yes.
Okay.
So we
Okay.
don't mention the depth in the we may not mention the depth in the question explicitly. So that can be inferred from my depth of my input.
Okay. Yes, sir. Yes, sir. Okay, sir. I understand. It was easy.
Okay.
Okay.
Okay. Thanks, Aditya, and thanks, Mukesh, for
Thank
joining
you.
the session.
Okay. Thank you.
All the best for your examination.
Thank you. Thank you.
Thank you.
So if you have any doubts, please post it in the discourse.
Yeah, I will
Okay.
post it in
Okay, sir.
WhatsApp chat. Yeah. Thank you.
Yeah.
Thank
Yeah.
you.
Bye. Bye, Aditya. Bye,
Bye.
Mukesh.
Bye.
Good job.